So in this example, a particle moves along a line so that its position at a time t greater than or equal to 0 is given by the function where s is measured in meters and meters, and t is measured in seconds. Okay, so I have a position function. Now part A, find the displacement of the particle during the first 2 seconds. What does displacement mean? Well, position is, you just plug in a t value and you get a position. The displacement is just how far it's traveled. So we can just say for part A, the displacement would be s of 2, whatever it is at 2, subtract whatever it is at 0. So that is the displacement. It's just how much it has moved. So at 2, what do we have? 2 squared is 4 minus 8, right? 4 minus 8 is negative 4, plus 3 is negative 1. And then we have to plug in the 0. Well, displacement we're subtracting, so that's subtraction. And then that would be positive 3. So the displacement is negative 4. That just means, like, negative, it means to the left side, yeah? Moved left 4 units. The displacement is negative 4, or you could say left 4 units. Okay, very good. This one says finds the average velocity of the particle during the first 4 seconds. Now some people might think, oh, you just take the velocity function and you take the average. Well, not really. Remember, if we have a position function, and we take the slope of the secant line, that's the average rate of change of position. Well, the average rate of change of position is average velocity. So it gets kind of confusing. You can think of it this way, though. I think most people would know, well, if you do the instantaneous rate of change of position, that gives you velocity, right? The instantaneous rate of change would be the velocity. So you kind of think, well, the average rate of change, this curve here would be the position function. So really all we have to do is get the average rate of change, do the slope formula. We're finding the slope of the secant line for the position function. So I would do, it says for the first 4 seconds, that would mean I would have s of 4 minus s of 0 divided by 4 minus 0. Now you'd think, like, wait, that doesn't make sense. Why we're using position when we're talking about velocity? It becomes velocity. Remember, this is like an estimate for the derivative. The derivative would be an instantaneous rate of change. That would be at a single point. So this gives us the average velocity. The average rate of change of the position is the average velocity. So let's enough about that talking. Plug in a 4. What do we get? That would be a 3. Right? If I plug in a 4, that's 16 minus 16 is nothing, and then it'll be 3. Okay. And then minus, well, that's the minus there. And then s of 0 is 3. Oh, 0 over 4. So this is 0. So the average velocity in the first 4 seconds is 0. And let's think about the units. Here, if I just have s, that's position in meters, right? It says in meters. So if I have this in meters, this would be seconds, meters per second. Oh, yeah, it is velocity. Meters per second. This displacement, that would just be meters. You could say, if that's ugly. You could say that's ugly, yes. It's ugly, I said it, all right. Moving on to part C. Find the instantaneous velocity of the particle at when t equals 4. That just means take the derivative of this to get the velocity function and then actually plug in 4. And I'll just use my power rules there, 2t minus 4, and I would plug in a 4, right, and I get 8 minus 4, that is 4. And remember, it is meters per second, so I have meters per second there. Part D, what is part D? Find the acceleration of the particle when t equals 4. Okay, same thing, I just take the derivative of that, v of t, v prime of t, or a of t. Remember, derivative of velocity is acceleration. That would be 2. and it's a constant acceleration. So, and then we have meters per second squared. Those are the units. And then it says, describe the motion of the particle. So I think the easiest thing to do would be to graph the position function. So let's say E. What does the position function look like? Well, it's a parabola. It's this. So we'll have one axis, the x-axis, being t. So it's the t-axis. Oh, it's t time. It looks like a z. A z's? No. A z. A z's on sour? No. And then this would be position s. So what does this look like? Well, it's a parabola opening upwards, and maybe I could, do we factor this and solve? No. So I can solve for the intercepts, the x-intercept and the y-intercept. Do I need to do it by hand? I'm just going to draw it. This you can get in a calculator or look up. The x-intercepts are 1 and 3. And the y-intercept is 3. 1, 2, 3. So these look like, oh, and the vertex is -1, comma. No, sorry, 2, comma, -1. I think. And then so, shoot. I missed, but oh well. Actually, this part isn't even on the graph because, and I did it poorly. That's better. Because t can't be less than 0. So, describe the motion. The particle is moving forwards, right? No, this is not the velocity graph anymore. Remember, this is talking about your position, right? This is position now. Okay, so let's think. Well, I'm starting out at a position at 3, it looks like. Am I starting? Yeah, that's what I got. I'm starting out at 3. And I'm moving to 1. I'm moving to a position of 1. Okay. And then I move to a position of... Oh, sorry, no. This is not a... I screwed it up. At t equals 1, my position is 0. So I start out at +3, and then I go backwards to 0. Oh, this is actually what... This is describing the motion. So you can just write this. So I start... The particle starts at 3, and then it goes to 0... on the line, wherever that is, and then it goes back. It's moving backwards because it starts at 3, goes to 0. Then it goes to -1, so it's back -1 unit past the origin, wherever that is, and that happens at 2 seconds. And then it starts to move forward, so it goes from -1 to 0, and that happens at t equals 3. And then it just moves forward after that for the rest of the time. So that's the description of the motion. At what t values does the particle change direction? Well, it's going from 3 to 0 to -1, so it's going in one direction. So that means at t equals 2, it changes around and goes from negative, and it starts to increase. So that would be at 2. Right? At what values of t does a particle change directions? That's only at t equals 2. Alright, I'm done with this. That's that problem. I don't remember what example.